José Hernández from CARTIF, and I would like to apologize for not being there. It was impossible to attend the conference. It's a pity because it's the third year I'm in this conference, and it's a really amazing conference, but it was impossible to be there. Anyway, I would like to present online this paper called Hybrid Digital Twin for Performance-Based Control Evaluation in Hydrogen Facilities, and I would like to thank my colleagues that are in the list of authors, and I will do my best to present this paper in this way. Basically, what I would like to present is, first of all, to define what is a technical environmental facility, our hydrogen-based TEF, what is our approach for the digital twin, for the hybrid digital twin, in order to run these experiments, the KPIs that we are included in this TEF in order to be analyzed according to the different scenarios that we have, the combination of time series and contextual data in order to provide a better performance information in order to have this hybrid digital twin, and finally a set of conclusions of this work. Basically, starting with the definition of a TEF, we can say that a TEF is a controlled realistic environment where advanced technologies, like for instance artificial intelligence, can be tested, validated, and optimized before real-world environment. In other words, saying that we have a virtual replica of a physical environment where we can test different conditions, constraints, and technologies without compromising the physical assets and the physical limits of the different systems. In this sense, at F can be said that we have the physical environment, that this is our real facility. In this case, our real facility is composed of a hydrogen electrolyzer, batteries, a fuel cell, an storage, photovoltaic, etc. And using data, we can convert or transform this real facility in a digital twin where we can provide different scenarios, or we can run different scenarios under an uncontrolled and safe environment. We can enable different artificial intelligence evaluation and different algorithms, different configurations, etc., without compromising the real assets. Of course, we accelerate innovation because we can, in fact, doing the things quickly, and we can test and validate different strategies. So in this sense, exploring scenarios, what if scenarios, what if results, and so on. So this is the real objective of a technology, of a TEF, let's say. And in our case, as I was anticipating before, this hydrogen-based testing facility is composed of different systems. First of all, and let me say that it's a hybrid hydrogen, electric, and thermal test platform. Everything done in order to test the AI-driven control strategies, and the physical assets can be summarized in the list that we have here: the electrolyzer, the fuel cell, in order to co-generate and provide this dynamic operational testing. We have storage in two waves: in the first of all hydrogen storage, but also metal hydride storage, in order to have this renewable coupling. Of course, we have thermal analytical systems, the loads, the heat pumps, the water tank, and the heater. And we also have some system for monitoring, control platform based on PLCs and Node-RED, real-time data, and so on, in order to support these scenarios to be simulated. Here you can see some pictures of the real scenario, so you see different systems of the real asset, as well as the monitoring system that is included in our TEF. So here you see the real environment that is later on translated into the virtual replica of the system. And then how our hybrid digital twin is composed. So in this sense, what we have done is we have the system data of the hydrogen system based on different experiments and different monitoring data, and we can train different models that are at the end different real assets in virtual replicas models. So in this sense, we have the digital twin composed of these models that are individual assets. I will explain better in the next slide. But the important thing here is that we have the data within the model, within the model trained, and we have the models within our digital twin, and with different algorithms we are able to balance the energy between all the systems in order to provide an optimized recommendation about how to use the assets. And of course, we have some flexibility and freedom for the users. First of all, about the renewable energy forecasting, basically the PV, the photovoltaic systems forecasting, in order to know the amount of energy that we count on from the PV systems, and the thermal and electrical load forecasting. So in this sense, we can adapt the renewable energy system that we have combined with the hybrid hydrogen system in order to cover the different thermal and electrical loads that we have in our system. So combining all this equipment, we can run different scenarios and to not only to optimize the energy that is generated, but also to optimize the sizing of the system. Providing more details, we have the data that I mentioned before, and for the model training, we have like two approaches that are combined together. So we have the data, and we can provide data-driven models, that is the machine learning model, traditional models, but we have also physical models for those systems that we don't have enough data. If we merge and combine both systems, we can have the GRI models or the GRI approach, combining physical and data-driven models. So, and you can see in the the detailed hybrid digital twin that we have in white the data-driven model. So we have the batteries plus the hydrogen system, the fuel cell, and the electrolyzer based on data. So we are able to train different machine learning models. But on the other hand, in red and yellow, you have the physical models. The reason is, first of all, the refrigerator is not installed, so it's simulated based on mathematical models. And the heat pump and the thermal inertia tank, we don't count on enough data because at the end, these systems are not providing water or heating system or heating energy to any part of the building. So it's a laboratory test. So the heat pump is not working. So we don't have data about the COP, the performance of the system. So that's why we need to simulate them. And this is the way that we create this hybrid digital twin for this experiment and how to deal with them. At the end, these algorithms will provide some strategies in order to optimize the energy balance of the different systems, and we have the current control strategies that are working in the system. So basically, our AI-based strategies will be overwriting the current control strategies in order to provide the different control strategies of the hybrid system. This will deal with some recommendation how to use the different elements that we have in the network and optimize the real work. Of course, this can be done over actuators, but the objective is not to actuate over the system. The objective is to provide the recommendation to the energy managers in order to optimize the energy or to learn about how the system is performing and taking the limits of the system that we have. And how to validate these algorithms? So basically, we have three levels of KPIs. So first of all, we have the model calibration system. In this sense, how the model or the accuracy of the model, the response time, and the data completeness. So in order to know which data, which type of models we have, and the accuracy of these models, we have the energy integration and flexibility analysis based on the how we can couple different energy systems, what is the flexibility on the thermal electric system that we have, and last but not least, the AI-based predictive control optimization in order to know the accuracy of the prediction, energy cost, the ratio of the hydrogen system working. So basically know how the system is performing as a whole thanks to this AI-based predictive analytics. So, but also we have, but we need to count on data, and the data is we are measuring different elements with sensors, and we have an equity broker collecting the data, node rate, and InfluxDB system in order to collect this data, and of course a dashboard and visualization tool that is sending feedback to the system when an actuation is performed. Basically, this is the monitoring architecture that we have in the system in order to collect the data to train the models. But we have also contextual data, that is the topology, the constraints, the asset info, specifications, and so on. So we need to create this control environment. So to do so, we need to not only maintain series data, but also to contextualize and enrich the data. And that's why we have two repositories. First of all, the time series repository that I showed you before with the InfluxDB, but we are also providing this contextual data repository based on knowledge graph and ontologies in order to support all this information that provides contextual information and allow us to configure, parameterize, and customize the different elements and the different systems that we have in the system. In this sense, we have the two complementary data types. First of all, the dynamic behavior of the system, but the structure and the topology by itself. In this sense, we have the real-time measurement composed by power, temperature, and other systems, but also the forecast systems. And also, as I mentioned before, the contextual data, including assets, configuration, the constraints, the topology, etc., that are combined together to provide a unified data model that compose assets, variables, and observations. And in order to have that, or to conclude that every data has, or every data point has meaning by themselves. So we create this mapping concept that's saying that each measurement is composed by asset, a variable, a time, and a value. So it's not only time series value, it's also a enriched time series value. But for that, we need a synchronization mechanism that is based on three levels. The assets IDs, all energy asset has its own ID that should be synchronized between the two repositories. We have the alignment in time because we need to know when the measure is taken, and the semantic tagging in order to know which asset belongs to which system and which measure belongs to which sensor and asset. In this sense, we can enrich this data. And here you see the time series data that is being used for this sense in order to have the information. And in order to conclude with this work, at the moment we are in the initial phase of this, so with the conclusions and the results will be later, but we have to say that these hybrid digital twins provide a realistic and scalable experimentation in these hydrogen-based tests. We're able to combine physics plus data in order to improve the accuracy and robustness of the systems. We integrate different data assets in order to enrich and provide meaning to this simulation and this scenario simulation. And we can support the performance-based evaluation and control strategies under the best scenarios. So we're providing a way to analyze and to simulate different strategies in a safe environment. And of course, last but not least, we can accelerate the development of this low energy carbon system that will support this climate change mitigation. That's all from my side. So I would like just to conclude this presentation saying that this work is the foundation for using digital twins, not only the way that we are using right now, but as a virtual environment to experiment and for the next generation energy systems. And that's all from my side. So sorry again for not being there, but if you have questions, comments, please don't hesitate to write me in this mail and to ask any question or any doubt that you have for this work. Thank you very much and have a nice day.